In this lesson, we are going to talk about continuity. And there is a very rigorous definition for continuity. However, before we get to the definition, I want to go through the intuitive meaning of continuity. That way, when we go through the rigorous definition, it will make more sense. So, for the intuitive meaning of continuity, it just means that if you look at the graph, you can trace the entire graph without lifting your pencil. So in other words, when we look at the graph, there's no breaks, jumps, asymptotes, or holes. So for example, if I had a graph that had a hole in it, when I go to trace that graph, I would have to pick up my pencil to jump over the hole and keep going. So there's a break in the graph, which means it's not continuous in the intuitive sense. Now, in order for it to be considered continuous by the definition, three things must happen, and this is very, very important. So the first thing that needs to happen, if we're looking at a specific point and we want to see if it's continuous at that point on the function, the value of that point must exist. That value at x equals a has to be defined. So, for example, if we look at this picture I just drew up here, if this was labeled as point A, this would not be defined. There's no value there. This would not be continuous based on just the first part alone. And in order for a function to be continuous, all three of these properties has to be satisfied. The value of the point must exist. Then the next one is the two-sided limit must exist. In other words, the limit from the left and the limit from the right must exist and be the same. Okay, that's the two-sided limit. It must exist. And then the third property that has to happen in order for this to be considered continuous at point A is the value of the function must be equivalent to the limit. You could have a situation that looks like this, where you could have a function and you could have a limit. Let's say this is the point A, and let's say this is L for limit. You could have the limit be L, and that exists. However, I could up here have the value of the function at, say, 5. So there's a hole here, but the value of the function is somewhere else. And so this would be discontinuous. By the intuitive understanding, there's a break in the graph. But by the rigorous definition, it wouldn't exist because the value of the function and the limit at that value of x, they are not the same. If any one of these fails, then the function just isn't continuous. So let's look at the first example. So using the definition, determine whether the function f of x squared minus 4 over x minus 2 is continuous at x equals 2. And it says justify your conclusion. Well, let's leave the properties showing so we can look at them. So we want to see if the function is continuous at x equals 2. Well, looking at the very first property, is f of a defined? In this case, a is 2. That's the point that we're looking at. Is this defined? If I plug in 2, does the value of the function exist? And without even going any further through the list of properties that have to happen in order for this to be continuous, it fails in the first one. So we can say, just by looking at the first one, we can say it is not continuous at x equals 2 because f of 2 is not defined. Okay, looking at the next example, we're looking at a piecewise function, and the question is asking us, is this continuous at x equals 3? So we want to go through the list of properties and make sure all the properties are satisfied. So the first property is, we want to see, for property 1, does f of 3 exist? Is it defined? Well, if I take x equals 3 and I plug in 3 into this piecewise function, I want to make sure, first of all, because this is a piecewise function, I'm plugging it into the correct piece. The piece that contains the value x equals 3 is the first piece. So I'm going to plug in 3 into the negative x squared plus 4. So f of 3 is equal to negative 3 squared plus 4, which gives me negative 9 plus 4, which is equal to negative 5. The first property passes. The value of the function exists at x equals 3. The next step is to see if the limit exists. So, and we want to make sure it's the two-sided limit. I want to see if the limit coming from the right of 3 exists, and that it equals the limit as x approaches 3 from the left. So if I find the limit of f of x as x approaches 3 from the right, I want to look at the piece where x is greater than 3. So if I plug in 3 into 4x minus 8, that's going to give me 4. If I want to see what happens at 3 coming from the left, I want to look to see where x is less than 3 as we get closer and closer to 3 from the left. So if I plug in 3 into the other piece, the minus x squared plus 4, that's going to give me negative 5. So this fails. So the two-sided limit doesn't exist. So we would say that this is not continuous at x equals 3 because the limit as x approaches 3 of the function does not exist. It's the two-sided limit. The one-sided limits exist, but the two-sided doesn't. And if we take a quick peek at the graph, if you were to graph this, just a quick sketch, it would look something like this, where we have a parabola, and at 3 it stops, and then we have a line, 4x minus 8 when x is greater than 3, that doesn't include 3, so we would have a picture that looks like this. So coming from the right as we approach 3, that's why this is negative 5 down here, and then coming from the right, it would be a different value, which would be 4. Okay, the next example has us looking at a piecewise function again, and we want to see if the function is continuous at x equals 0, and of course we have to justify our conclusion using the definition. So we always start with the first property that has to be satisfied. Does the function exist at the point that we are investigating, which is 0? Does f of 0 exist? Well, if I find f of 0, based on the piecewise function, when x is 0, the value of the function is 1. So this is satisfied. The second property we want to look at is, does the limit as x approaches 0 of f of x exist? So we want to see if coming from the left and coming from the right exist, and if they're the same, then the two-sided limit exists. So when we first look at the limit as x approaches 0 from the left of f of x, if we look at this piecewise function, anything that is not 0 uses this piece here. I'll highlight it in green. And if it is 0, then the value of the function is just 1. So coming from the left and the right, we're going to be using the same piece, sine of x over x. So from the first lesson, we talked about this being a very famous limit. The limit as x approaches 0 of sine x over x, that's equivalent to 1. And you should keep that on your reference sheet because we'll use that quite a bit. So coming from the left, it's going to be 1. Coming from the right, since you're also looking at positive values, and that's not equal to 0, so we're going to use sine of x over x again. Coming from the right, we know that f of x is equal to 1. So the two-sided limit exists. So that second property passes. Now the third property says that we have to check that the value of the function has to be equal to the limit of the function at that point. And we said in the first step, the value of the function is 1. In the second step, we said the value of the limit was 1. So this property passes as well. Since all three properties pass, this is definitely continuous at x equals 0. So as we've seen through these different examples, the discontinuities take on different appearances. We could have a hole, we can have a break in the graph, a jump, an asymptote, right? There's different kinds of discontinuities. And so we're going to look now at the different types and how to classify them. So if we look at these three graphs down here, we have graph A, B, and C. Graph A is an example of a removable discontinuity at x equals A because there is a hole at x equals A. F of A is not defined. Now, for B and C, these are both examples of discontinuities where pieces of the function do not line up. So there's a jump here, but if I were to trace this one, there's also a jump from here to here. The difference between these two, the infinite discontinuity has an asymptote at x equals A. So that's the point that you're looking at, that there would be a discontinuity at x equals A. A jump discontinuity is when there's just a break in the graph and the pieces don't line up, but there's no asymptote there that's splitting it up. It's not an infinite distance between them. So that's called a jump discontinuity when there's a finite distance between the pieces of the graph. So we are going to practice classifying the discontinuity. So in this case, we have x squared minus 4 over x minus 2. Now if we look at this function, I can factor this as x minus 2, x plus 2 over x minus 2. And because we factored it and we have the same factor on the top and the bottom, I can get rid of this. And so after simplification, I have x plus 2. So if I take a look at the graph of x squared minus 4 over x minus 2, I would get a picture that looks like this. And then if I graph x plus 2, the line, I would get this picture. This is called a removable discontinuity because the limit exists It's just a hold. So we're going to call this removable. Okay, the next example is an example of a jump continuity, because if I were to graph this, just a sketch, so we're going to get something that looks like this. We have the upside down parabola, like this. And then for the second piece, we have the line for x minus 8 that looks like this. So if I were to trace the graph from left to right, I'm tracing the parabola, and then I stop and I jump to the next piece. This is called a jump discontinuity. There's a jump from one piece to the other. Okay, last example, we have the rational function x plus 2 over x plus 1. If we draw a sketch of this, we're going to have a vertical asymptote at x equals -1. We have an x-intercept at x equals -2. And so we're going to have a horizontal asymptote at x equals 1. So this is where you have to think back to your college algebra class when you're graphing rational functions. So my picture, just a quick sketch, is going to look something like this. Now this is called an infinite discontinuity, because at x equals 1, we have an asymptote. So now that we talked about the concept of continuity at a point, we're going to now extend that idea and start talking about continuity over an interval. So we're going to talk about open intervals and closed intervals. If you recall, an open interval would look like this, where I use parentheses from x equals a to x equals b. Open means I'm not going to include the points a and b, but it's going to include everything in between. So this is an example of an open interval. And then a closed interval would look like this, where I would use brackets, because that means I'm including all the points between a and b, but I'm also including the endpoints a and b. So for this interval, I'm including the endpoints a and b, and this one's I'm not including the endpoints a and b. Okay, so when we talk about continuity over an open interval, we're talking about a continuity over an interval that looks like this, from like maybe parentheses 3 comma 4 parentheses. So from x equals 3 to x equals 4 as an example. So in order for an open interval to be continuous, all the points between a and b have to be continuous, every single point between there, but not necessarily the endpoint. So you could have like open holes and not be defined at the endpoints a and b. Now, if you want to be continuous over a closed interval, all the points between a and b need to be continuous, but also the points a and b also have to be continuous. So you have to include those endpoints in the continuity. So the limit coming from the right has to exist, and it has to be equivalent to the value of the function. And then for the endpoint b, the limit coming from the left has to exist, and it has to be equivalent to the value of the function at b. Okay, so let's look at the first example. we have a rational function here, x minus 1 over x squared minus x minus 2. And a rational function is going to be continuous everywhere except if there's like a hole or an asymptote. And if you think back to college algebra, when we talked about finding holes and asymptotes of rational functions, we had to first factor to find where there's holes or asymptotes. So if I factor the denominator, I have x times x minus 2. So for this example, we have no holes in the graph because I don't have a factor that's the same on the top and the bottom, which would create the hole. I do have two asymptotes. I have an asymptote at x equals 0, and I have an asymptote at x equals 2. So these are going to be those infinite discontinuities. And so everywhere else is going to be continuous. So I would say continuous from minus infinity up to 0. And I don't want to include 0 because remember that's a discontinuity. But everything up to 0 is okay. Union 0 to 2. Union, and then 2 to infinity. So we're skipping over 0 and 2. Those are our places that are discontinuous. But everywhere else is continuous. Okay, now looking at the next example, we have the square root of 4 minus x squared. And so from the limit laws, we know that the limit as x approaches a of 4 minus x squared is going to be equal to the square root of 4 minus a squared if we plug in a and do direct substitution. And that's going to work for all values between -2 and 2. The places that we're concerned about are those endpoints that we want to check. Okay, so we want to make sure that the limit coming from the right of -2 exists and that it's equal to the value of the function. As we approach -2 from the right, we're going to get a limit of 0. And we know that f of -2 is equal to 0. So that works, that endpoint works. Now, if we check the other endpoint, if we go the limit as x approaches 2 from the left of 4 minus x squared, that's equal to 0. And if I check the value of the function, I get 0. So that works. So we can say that this is continuous on all intervals between -2 and 2, including -2 and 2. So we can say it's on a closed interval. So now that we have talked about continuity quite a bit, I'm going to add another rule for our limit laws to our list. So this is something that can be added to our list from the previous section. We couldn't quite add it into our list yet because we needed to discuss continuity in order to discuss this theorem or this rule for the limit laws. So this limit law regards composition functions. So that's when you take a function and you plug it into another function. So if I'm taking the limit of a composition function, that limit would be equal to f of L, where the inner function has a limit of L, and I just take that limit and plug it into the outer function. Now that works provided that the outer function, your f, is continuous at that point L, and that the limit exists for g of x. So that's kind of a mouthful. So let's walk through an example to show you how this works. Okay, so we have a composition function here. We have the outer function, which is cosine, and we'll call that our f of x. And then we have the inner function, which is just a linear function, x minus pi over 2. So if we look to see what the limit of the inner function is as x approaches pi over 2, we get 0. So the limit for the inner function exists. Now the next question is that limit, this is our value of L from the theorem, is that limit L, is that point continuous on the outer function? So if you look at the graph of cosine, we know that cosine is that wave function, and there's no asymptotes or holes, and it goes on forever. So we know that cosine is continuous at that limit is 0. So because it's continuous at that limit for the inner function, I can say that the limit as x approaches pi over 2 of cosine of the composition function is equivalent to just plugging in that limit into the outer function, which is equal to 1. Okay, another theorem that we can talk about now that we're familiar with continuity is the intermediate value theorem. And this theorem is very useful for being able to identify intervals that have zeros on them. So let's first talk about what the intermediate value theorem is, and then we're going to apply it to a couple of examples. So the intermediate value theorem says that if f is continuous, and I have to stress that this has to be true or this theorem doesn't work. F has to be continuous over a closed bounded interval from a to b, okay? And if z is any real number between the two corresponding y values, f of a and f of b, then there has to be a number on that interval between a and b so that when I plug it in, I get out that value of z. So if we look at the picture and we look at our interval from a to b, if there is a value of z between the corresponding y values, then there has to be a value of c. So when I plug in c, I get out z. And this only works if it's continuous. Here's an example of why it possibly couldn't work if it was not continuous. Let's say I gave you this picture, A, B, and so this is f of A, and I'll say that this is f of B. And let's say the picture looks like this. Maybe it's a piecewise function, and it looks something like this. Now, for every value between f of a and f of b, if I pick some value z, there isn't necessarily a value of c that would give me a value between f of a and f of b because there's a break in the graph. So this is why this only works if it's continuous. Now, a really good application of this is being able to identify intervals where there are zeros. So now let's look at this first example below where it says show that f of x is equal to x minus cosine x has at least one zero. We know that this function is continuous. There's no asymptotes, holes in the graph, or any jumps. So this is definitely a continuous function. Now, if I find two values of y where it goes from positive to negative or negative to positive, I can use the intermediate value theorem to show that there is a zero on the intervals with the corresponding values of x. Now it has to be at least one zero, and there could be two, there could be three, but this theorem says there's at least one zero. Okay, so let's say I pick f of 0. That gives me negative 1. And let's say I pick f of pi over 2, that gives me pi over 2. So if I look at the interval from 0 to pi over 2, there's my x's from 0 to pi over 2, and my corresponding y's would be -1 to pi over 2. So somewhere between -1 and pi over 2, that function has to hit the x-axis because it goes from negative to positive. Because it's continuous, there's no breaks in the graph, so it has to cross over the x-axis at some point. So I know that there exists a value of c such that f of c would give me 0. And again, that is because this function is continuous and I'm going from a negative number to a positive number, so somewhere in between here, since there's no breaks or holes or asymptotes in the graph, I know that somewhere in there you have to hit the y value of 0, which means you hit the x-axis, which means you have a 0. So, by the intermediate value theorem, we know there's a value of c that when I plug it into the function, I would get out 0. So, we can say by the, I'm going to abbreviate, intermediate value theorem, there is at least 1 0 on the interval from 0 to pi over 2. Sorry, I'm running out of room here. So we just used the intermediate value theorem to say that I know there's at least 1 0 on the interval from 0 to pi over 2. Okay, let's do another example. If f of x is continuous over the interval from 0 to 2, so here's the key thing that we need to be able to use the intermediate value theorem. And the problem is telling us it is continuous and it's on the interval from 0 to 2, the closed interval. F of 0 is positive and f of 2 is positive. Can we use the intermediate value theorem to conclude that f of x has no zeros in the interval 0 to 2? That would be false. If I pick a different value, let's say I pick f of 1. If I pick f of 1, maybe that value is negative. And then by the intermediate value theorem, I could say that there is a 0 between 0 and 1, which lies on the interval from 0 to 2. So we can say this is not true by counterexample. So let's say our counterexample is, what if f of 1 is equal to -2? Then we have f of 0, which is positive, and we have f of 1, which is negative. And then we can say by the intermediate value theorem, there has to be a 0 between 0 and 1. And therefore, we can't say that this is a true statement. Okay, last example. For the function 1 over x, f of -1 is equal to -1, and f of 1 is equal to 1. Can we conclude that f of x has a 0 on the interval from -1 to 1? We would say no, because on the interval from -1 to 1, it is not continuous. We have to have a continuous function. It has to be continuous on that interval for this to work. And if you recall, the graph of 1 over x looks like this, where there's an asymptote at x equals 0, right? Because you can't divide by 0. 1 over 0 does not exist, and that's where our asymptote occurs. So if f of 1 is 1, so we have a point here, and f of -1 is -1, and we have that point here, we do not have a 0 on that interval. We have an asymptote here instead, even though we have a positive here and a negative value here for the function value. Because the function is not continuous on that closed interval, we cannot for sure say that there is a zero because of the asymptote. There's a break in the graph. So this is another example of why it has to be continuous in order for this theorem to work.